Good morning. Today we're going to talk about more relations. In particular, we're going to talk about equivalence relations. So I mentioned them last class, and now we're really going to go in depth. Before I begin today's lecture, are there any questions about the material from the other day? So the last problem that we were working on, the last practice problem, we're going to go over today. And I've changed it slightly. So this time I think there should be no confusion as to what I mean. I hope so, at least. Okay. Um, no questions? Then let's jump in. So the first announcement is to remind you that your homework is due tomorrow at 11:59 p.m. That's Friday the 19th. And this is all the homework on chapter 4. Quiz 4 is next Thursday, March 25th, during class right now from 10:45 to 12:05. That must be handed in via Gradescope by 12:35. Now, this is just for the record. I'm not saying anyone does this, but I want to make sure you all understand that if you submit an exam by email after 12:35, with the excuse that says, oh, my scanner didn't work, or I couldn't get it turned into PDF, or for some reason I couldn't upload, unknown reason why, it won't be accepted. Okay. You should be attempting to scan. There's a half hour from 12:05 to 12:35 during which you're supposed to be dealing with scanning and uploading and all the rest of the issues. So if you encounter a problem, it should be during that time. And if it's during that time, you're supposed to send an email or to send a note via Piazza to instructors and state exactly what's happening. Okay, if you wait till after, it means that you didn't try doing anything into the last few seconds. And that's not acceptable. The reason you have that half hour is to take care of all these issues and be able to let me know. Is that clear to everybody? Good. Okay, if you do have a legitimate emergency, if something comes up, which can happen, then you should notify the teaching staff via note to Piazza, again, to instructors as soon as possible. Typically, I would hope that would be before the exam if something happens that morning, during the exam if, God forbid, something happens then. And if you have problems that are legit, like your internet goes out, use your phone. Okay, I need a real excuse that it's not just I'm saying my internet went out, but you have a note or something from Comcast saying that your facility broke down or your apartment building, someone cut a wire or whatever. Your writing it is not quite enough. Okay, so quiz review. Today we have quiz review. This exam we have quiz review on Tuesday from 5 to 6 with Nancy. And then her regular office hours continue until 7. So there's individual time and group time. And then on Wednesday, from 3 to 4, there'll be a review with Ben, and his regular office hours will continue from 4 to 5. So as you know already, I hope that you get to them by going to the respective Zoom links under the weekly office hours module page in Canvas. They'll disable the waiting room and everybody will go in for the first hour who wants to attend the review. Okay, exam on Thursday, reviews Tuesday, review Wednesday, exam Thursday. All right, the material, exam 4, quiz 4 will be on all the material in sections 4.1 to 4.5. Whether it's in the book, whether it's covered in the pre-recorded lectures, or whether it's in class. So if you have questions, please don't hesitate to ask. That's what we're for. Okay, are there any questions about the exam next week? Or anything about the review or anything else? Okay, in that case, let's jump into the material. So the first review problem that we have is to prove that the integers and the natural numbers have the same cardinality. Now remember, what are the natural numbers again? So the natural numbers are equal to all the positive integers plus 0. Okay, now I know some of you, maybe in other classes, have seen that the natural numbers consist of all the positive integers. This is defined differently. Different book authors and different users define it differently. Our job is to know what the definition is and use it appropriately. And this book, and so this class, will be consistent with the book and define it as all the positive integers plus 0. Okay, any questions? All right, so we're supposed to prove that two infinite sets have the same cardinality. And in order to do that, remember, there was a theorem that said, well, definition, that said two sets have the same cardinality if you have a function that has an inverse on them. So that's our job. We need to find a function that is invertible that maps from all of the integers to the positive integers. Does everybody understand that? Okay, so we're going to take the easiest thing we can, and in order to do that, we're going to map basically a function that takes all the odd integers and maps them to the even natural numbers. And then we're going to take all the positive integers and map them to the odd natural numbers. So let's start with that. Let's say, suppose we're defining f of n, where n is in z, any integer in z. Then we're going to say, what is that equal to? Well, if n is negative or equal to 0, we're going to map it to minus 2n. Okay, the minus makes it a positive number if n is negative, and then 2 times that. That makes it even. If n is 0, then negative 2 times 0 is 0, and we're set. That's not a problem. Okay, and now we want to map all of the all of the positive integers to the odds. Now, you might say, well, that's 2n. We might say that's 2n plus 1, but that doesn't work because we've already mapped 0. And 0 is n even. It's going to map to the even. So it's got to be 2n minus 1. So if we look at that, if n is 1, it maps to 1 times 2 minus 1, or 1. If n is 2, it maps to 2 times 2 is 4, minus 1 is 3. Okay? So that's our mapping. And how are we going to prove that it's invertible? Well, we have to find the inverse. Okay, so now we're going to say, let g of m, let's say. Now, m here is a natural number. And we're going to let g of m equal, so what do you think we're going to do? We're going to say it's minus m over 2 if m is even. And it's equal to m plus 1. It's a plus 1 over 2 if m is odd. Okay? Okay, now we can look at that and we can say, well, we could have proved it was invertible. How could we have proved it was invertible without finding the inverse? Well, we could prove that f is 1-to-1 and onto. Remember, a bijection is 1-to-1 and onto, and a bijection is always invertible. Okay, and that means that the set Z and the set N would have the same cardinality. That's another way of proving it. So let's look and say, suppose we wanted to prove that F was 1-to-1 and onto. How would we do that? This is just a sampling so we remember how to prove 1-to-1 and onto. Does anybody have a clue? Suppose we want to prove F is 1-to-1. How are we going to do that?
Suppose we have like X and Y given and that they result in the same thing, and then prove that means they have to be the same thing.
That's exactly right. So we're going to take X and Y and Z such that F of X equals F of Y. Okay, then let's say F of X is either even or odd. Okay, if even, then there exists M such that F of X is equal to, I'm sorry, it doesn't have an X. X is equal to 2X is equal to 2Y minus 2X minus 2Y. Is equal to F of Y. And that implies that X equals Y. Just that statement right there. We can divide through both sides by -2. If F of X is odd, then by the definition, F of X is equal to 2X minus 1, which is equal to 2Y minus 1, which is equal to G of Y. So if we add 1 to both sides and then divide by 2, then X equals Y. Okay, finally, how would we prove onto? Onto says, let X be in the natural numbers. Now we're starting with the codomain. We start with the codomain and we say, then the same thing, X is either even or odd. Yes, does someone have a question?
Nope, sorry, I was talking to my dog and I was accidentally unmuted.
Okay. Okay, is even or odd. If even, then there exists M in Z such that X is equal to 2M. Okay, let N be equal to negative 2M. No, I'm sorry, negative M. Let N be equal to negative M. Then X is equal to negative 2 times N. Because negative of a negative is the original, the double negative property. Then what do we know? Then F of N is equal to X. Is an integer. Okay, and we would prove it similarly if X is odd. We'd go through the same thing and show that there exists an N for which this works and that F of N is equal to X. Okay, that's 1-to-1 and onto. So remember, 1-to-1, we start out and we say, suppose there are 2 elements of the domain that map to the same place in the codomain. If we're proving onto, we say pick an element out of the codomain and find an element in the domain that maps onto it. Britton, yes.
So for f of n, when n is greater than 0, it seems to me like there's elements in the codomain that don't have an element in the domain that maps to them. For example,
Pick one.
like if you think of like an even number, like 2n minus 1, if you plug
That's
how
an
do you
odd number, 2n minus 1.
But like, aren't we trying to figure out, isn't the codomain include anything, any
Yeah, oh yes. So
any natural number?
okay. So let's pick an odd number. Let x be odd. Be odd. Sorry about that. Then x is equal to 2k plus 1. That's the definition of odd, right?
Yeah.
Okay, good. Then that's also equal to 2 times k plus 1 minus 1. True?
Yep.
Okay. Let n equal to k plus 1. If k was positive, then n is positive, and f of n equals 2n minus 1. Okay? You see it?
Not exactly, but I'll have to go back and look at it later.
Yeah, sorry. Let's, I think I have a space here in case we need it. So let's say, well, pick any odd number if that helps. We're going to say let x be equal to, let's say 7. How's that for a nice odd number? Okay. Then we know that 2 times n plus 1 equals 7. So n equals 3. That's k, sorry, that's a k. Okay, true?
Yeah.
Okay, then 2 times 4 minus 1 is also equal to 7. That's k plus 1. Okay.
Okay, I see what you're saying.
Okay, so that means f of 4 is equal to 7. That's the definition, because 4 is a positive number, and we map the positive number by f onto 2 times that number minus 1. David, yes.
So on the last slide, we had the thing about n had to be greater than 0, right?
Wait, for what? Well, yeah,
For,
yes, because
So
we're
what
not,
happens-
we're taking an element of the codomain.
yeah, so what happens if you had -7?
-7 isn't in the codomain.
Okay.
Codomain is greater than or equal to 0. I don't have to map anything onto a negative number because that's not the codomain.
But weren't we trying to have this represent all integers? I think that's where I'm confused is.
Okay, let's start out. We are mapping from all the integers to the natural numbers. That's F. Okay, we want to show that the integers and the natural numbers have the same cardinality. So we have a mapping that we're showing is a bijection. And if it's a bijection, it means that they have the same cardinality. Okay?
Yeah, that makes sense now. Thanks. I was just wondering, like, was this all of them? No, it's only a subset of them to prove that it's invertible because that subset includes, yeah.
Invertible says 1-to-1. So when we're starting with 1-to-1, we always start in the domain and prove it maps 1-to-1. And then when we're trying to prove onto, then we start in the codomain and find something in the domain. So a one-to-one mapping does not have to be onto. Just remember that, okay? If we have a one-to-one mapping of a function of a domain to itself that is not onto, then that domain is infinite. Okay?
Yeah, that just leads me to another question. Could you then say that the inverse function does not exist? Because the inverse function would not be onto. Or are we representing a
Well,
subset?
if you don't have something that is onto, then the inverse function doesn't exist. That's correct. Okay?
Because the inverse function couldn't return a number that was like a negative odd or positive even, right? So wouldn't it therefore not?
This does have an inverse function. This absolutely has an inverse function because it's one-to-one and onto. Okay, so I can pick an element of the codomain and map backwards onto the domain by that, but we also showed it was one-to-one and onto. Now, it is also the case, remember we had the Cantor Bernstein theorem, and what did that say? That said I can have a function that's one-to-one from the domain to the codomain, and a function that's one-to-one from the codomain to the domain. They don't have to be inverses. But if I have that, then they have the same cardinality. Okay, so you have to be careful saying, well, gee, if the inverse doesn't exist, then they can't have the same cardinality. That's not true. It just means that the function you picked doesn't have an inverse. Okay, when you're dealing with infinite functions, things are a little different.
So then with an infinite function, if I understand correctly,
I'm sorry, an infinite domain, sorry.
with an infinite domain, you could have a function that is one-to-one and onto, but its inverse isn't.
No,
Is it
if it's
inverse
one-to-one
isn't
and onto, it's fine. It has an inverse. If it's one-to-one but not onto, for example, if I mapped all of the integers onto all of the integers by just multiplying by 2, I would map them onto all the positive integers. There would not be, that would not have an inverse that goes from the integers back because I didn't map onto all the integers. Okay. Does that make sense?
I'm just still confused if G of M, if you plugged in, how you would get back all integers from G, unless.
Well,
yeah.
Pick an integer that you want. Okay, you want to prove that G is onto?
Yeah.
Good. Pick an integer, any integer, positive or negative.
Let's see now, negative M over 2. So negative M over 2 makes it a negative if it's even. I don't know. How about a positive even number? Try to get how would you get a positive even number out of the inverse function, out of G of M, if that makes sense?
How would I get a positive even number? Okay, so if I have a positive even number, say Q is a positive even number. Okay, so I want to find an N that's greater than or equal to 0 such that G of N is equal to Q. Okay. So let's go back to the definition of N, of G. And we have that positive even number. Here it is. There's a positive even number. So what does it say to do? It says that would mean minus N over 2 should be equal to Q. Okay, so that says minus N, remember Q is positive here, is equal to 2Q, where N is equal to minus 2Q. So I found a number that maps onto Q by G.
And this is where my question kind of arose, because isn't n supposed to be a member of the natural numbers, or is it supposed to be an integer?
N is greater than or equal to 0, so it's a natural number. And you're saying, how can that be? Well, remember, Q No, n is not greater than or equal to 0. N is greater than or equal to 0. But Q is not. You told me Q. Oh,
And that's a contradiction I've been finding, is that if the g of n is onto from natural numbers to integers with that formula, there's a contradiction in positive evens or negative odds.
n is a positive even number. Let me think about that. I will come back to that. Somewhere we made a mistake, and that's not the case, but I'll come back to that because I need to move on. So let's do this at the end of class, okay? And everybody can stick around if they want. We'll get it right then, okay? Let's prove that for every set of 5 integers, there's at least 2 numbers in the set Y, which is 3 to the A, 3 to the B, 3 to the C, and 3 to the D, 3 to the E that have the same ones digit. So how will we go about proving that? Well, let's start out and say, well, what are the possible, what are the possible ones digits? So I can have 3 to the 0, and the ones digit on that is 1. And I can have 3 to the 1, and the ones digit on that is 3. And I can have 3 to the 2, and the ones digit on that is 9. I can have 3 to the 3. Now we get into different territory. And the ones digit on that is 7. And then I can have 3 to the 4. And the ones digit on that is 1 again. And if we look at these things, when I say 3 to the 4, that's the 3 to the 5. The next one, that's the same as saying 3 to the 4 times 3. So the ones digit on that is going to be, that's like saying 3 times 80 plus 1, or 3 times 80 is 240 plus 3 times 1 is 3. So again, we're back to having a ones digit of 3. So we're going to see is that the possible 1 digits there are the numbers 1, 3, 9, and 7. Remember, order doesn't matter in a set. And they're the only possible ones digits because they just keep coming back now because of this kind of property. So the next time we would be saying 3 times 240 plus 3, and the ones digit would be the ones digit of 3 times 3, which would be 9 again. Okay, so would we be just cycling through these ones digits? Now the numbers get bigger and bigger, but the ones digits stay in those 4. So now I have 4 possible ones digits, and I have 5 integers. And I'm mapping the 1 digits in Y to those 4 integers. So what do you know that tells us anything about that? I have a mapping F that goes from Y to the set 1, 3, 9, 7. What do you know about that?
Can we apply the pigeonhole principle?
You bet. What does that say again?
It says that if you have a set that is,
The simplest version of it, you've got it. The simplest version of it says that if you're mapping n things onto, let's say, B boxes, you have this M times B plus 1. Okay, so we're mapping 5 things onto 4 boxes. So that says M plus 1, in this case 2, have to fall into the same box. At least 2. Okay. Let's move on. Is that okay? I just wanted to remind you that pigeonhole property comes up here. Okay, now let's remember from the last class, we had a bunch of definitions. We had a relation. Remember what a relation is. A relation is a function. What we have is a set of pairs on X cross X, if we have, or a set A cross A, that have a certain rule that defines them. And that rule defines whether they have other properties. And if it's a partial order, is defined as being reflexive, anti-symmetric, and transitive. A strict partial ordering is irreflexive, anti-symmetric, and transitive. A total ordering is a partial ordering that has the property every 2 elements of the set are related in some way. And a strict total ordering is a partial ordering and is a strict partial ordering. That means it's irreflexive, it's anti-symmetric, it's transitive, and all 2 elements of the set are related. Okay. And then remind you, this is all the way back from chapter 3, maybe? As for a set A, a partition of A is a set of sets that we're going to call S, and that's equal to, we have a bunch of sets in it, S1, S2, however many there are, of subsets of A such that each element, each set in script S is not empty. They're pairwise disjoint. They have no elements in common. And their union is the whole set A. That defines a partition. And each set is called a part of a partition. Okay. So we had a definition. Now we're going by what the book defines it as, that a set A and a relation R is an equivalence relation on A if there is a partition, script S of A, such that X and Y is in the relation, if and only if X and Y are in the same part of S. Okay, if and only if. Okay. Then we had a theorem. We actually had 2 theorems in the book, but I'm combining them into one. That says a relation on a set A is an equivalence relation if and only if it's reflexive, symmetric, and transitive. Now, if you look in other books, you might see the fact that other books might define an equivalence relation as being a relation that's reflexive, symmetric, and transitive, and then prove the other direction that that means it does a partition. Our book does it the opposite way, but it doesn't matter. When it says if and only if, it means that they're equivalent. Okay, so this definition that we have above is equivalent to saying that the relation is reflexive, transitive, and symmetric. Let's do an example right now. Find the partition of the integers induced by the relation T is the set of all A, B, and Z cross Z such that B minus A is divisible by 5. Okay, so that's the partition that we're looking for. B minus A is divisible by 5. Okay. So what do we know? Forget the B minus A for a minute. What do we know about when we see the word divisible by? We know that for any integer, for all integers x is equal to 5k plus r k, some integer, a different integer, and r greater than or equal to 0 and less than 5. We see that divisible there. Okay, so what do we have out of that? Okay, let's take the set T0 equal to the set of all integers. Let's say z in z, such that z is equivalent to 0 mod 5. Remember, z equivalent to 0 mod 5 means it has a remainder of 0. T1 is equal to the set of all z in z, such that z is equivalent to 1 mod 5. T2 is the set of all z in z, such that little z is equivalent to 2 mod 5. And T3 is equal to z in z, z equivalent to 3 mod 5. T4 is equal to z in z, such that z is equivalent to 4 mod 5. Okay. So is T equal to T0, T1, T2, T3, T4 a partition of Z? Yes? No? Is every integer inside? Yes. Does every integer have a unique representation? So we can't have an integer that has a remainder 0 and a remainder 3. Okay, so that means that pairwise, they're disjoint. They have no intersection. At least 0, 1, 2, 3, or 4 is got to be in each of those sets. So they're non-empty. That satisfies the requirements of a partition. Now, how is that related to this relation? That's the big question. So let's let A and B be two integers. Okay. Such that we know that A is equal to, say, 5k plus R1, and B is equal to 5m plus R2, right? Okay. And we know that B minus A, which is equal to 5k plus R1 minus 5m plus R2, which is equal to 5 times k minus m plus R1 minus R2, is equivalent to 0, is equal to 0. Why do we know it's equal to 0? Because we know 5 divides B minus A. So if 5 divides B minus A, R1 minus R2 has to be equal to 0. Okay, this is if A, B is an element of the relation T, then this has to be the case. So R1 has to equal R2. So what does that say? That says that if A, B is in the relation, then A and B are in the same part of the partition. Okay, that's the first thing that we had to prove from the definition. Okay, such that X and Y are in the same part of the partition. Now we have to prove the other side. We have to say they're in the relation. If they're in the relation, we have then they're in the same part of the partition. Now we say, suppose they're in the same part of the partition. Well, if they're in the same part of the partition, okay, if A and B are in the same part of our partition, call that T sub R, then A is equal to 5K plus R, and B is equal to 5M plus R for some K and M in integers, and that's by the definition, the divisibility theorem. That's how they were defined. So A minus B is equal to 5K plus R minus 5M plus R, which is equal to 5 times K minus M. And so A minus B is divisible by 5, which implies that A, B is in the relation. So we proved if they were in the relation, then they were in the same part of the partition. Then we proved if they're in the same part of the partition, then they're in the relation. And that satisfies this definition. So we use the definition to show that there is a partition. And what did that say? By the definition, that says T is an equivalence relation. Okay.
So if we're using those, sorry, I didn't raise my hand. If we're using those, or if we're using that definition of an equivalence relation, then we need to make sure we show both of those parts, since it's an if and only if.
Absolutely.
And then there's also the possibility of using the second
Yes.
the second way of proving it, where we say that it's asymmetric.
It's symmetric, not asymmetric.
Or symmetric,
Reflexive and transitive.
reflexive, and transitive. Yeah.
Those are the big three. RST. Reflexive, symmetric, and transitive. RST. All three. RST equals E in this case. So that's the key. I mean, you know, Einstein got F equals MA. We have E equals RST. Equivalence equals RST. Okay? Good. Let's try practice problem 5. So here we are. Prove that it's an equivalence relation using the definition. That's the partition if and only if. And then show it's reflexive, symmetric, and transitive. So here we're going to do both ways of showing it's an equivalence relation. Okay? Okay. So let's look at the possible elements just for the heck of it. So let's let B be some of the elements, okay? So tell me which ones are definitely not there. Is 1, 1 in that? So I have 1 minus 2.5 times 1 minus 2.5. So I have negative times negative, and that's a positive. So I have 1, 1. Is 1, 2? 1 minus 2.5, that's a negative. 2 minus 2.5, that's still negative. So I have negative times negative. Is that positive? Yes. So I have 1, 2. Okay. Is 1, 3 in the relation? I have 1 minus 2.5, that's negative, and 3 minus 2.5, that's positive. Negative times positive, what is that? That's negative, so that's not in the relation. And 1, 4 is not, because that's even more negative, and 1, 5, that's even more negative, so those aren't in it. What about 2, 1? Is 2, 1 in the relation? 2 minus 2.5 times 1 minus 2.5, negative times negative, that's in the relation. What about 2, 2? That's 2 minus 2.5 times 2 minus 2.5, negative times negative, that's positive. What about 2, 3? 2 minus 2.5 times 3 minus 2.5, that's negative times positive, that's negative, that's not in the relation. And again, 2 times all the rest, that can't be. So we have 1 and 2 are the integers that separately and together lead to negative times negative being a positive. Now, if I have negative times positive, that's always going to be negative. So if I pick a number, one of the numbers smaller than 2.5 and the other number bigger than 2.5, that can't be in the relation. Okay, so that's not in the relation. So then we have another collection, and the other collection, we'll call it C, and that's the set of cases where we have positive times positive. Okay, so what's positive times positive going to be? Well, we know they both have to lead to positive numbers there. So we have 3, 3, 3, 4, and 3, 5. And then we have 4, 3, 4, 4, and 4, 5. And then we have 5, 3, 5, 4, and 5, 5. Now, did I leave anything out? And the question would be, is the union is B union C equal to R? And I believe it is, okay? Because any other set of two numbers is going to be one smaller than 2.5 and the other bigger than 2.5. And so their product, when I take 2.5 away, will be negative. It'll be a positive times a negative. Okay, so this is the case. So we have something that gives me the whole relation. Okay, so what values from A are in B? Well, I have 1 and I have 2. And what values are in C? I have 3, I have 4, and I have 5. So is A1, A2, a partition of A? So that's the question. Well, is every element represented in the union of A1 and A2? I have 1, 2, 3, 4, 5. So they're all there. Is each set non-empty? Well, yeah, one has 2 elements, the other has 3. Is their intersection empty? Well, yeah, on that account too. We can look at that and see it. Okay, so that satisfies the requirement of a partition. Now, is it the partition induced by the relation R. First of all, is there a partition induced by R? And is it that one? Those are the questions. So let's look, how do I know if it's a partition induced by R? And that therefore R is an equivalence relation? Well, I know it to be the case if what? Any two elements in A are in the relation if and only if they're in the same part of the partition, if and only if. Okay, so let's say, suppose AB is in the relation. So A and B are in R and AB is in the relation. Then what do I know? Then A and B are, they're either in B or they're in C. Now, then, so let's see what happens. So if they're in different parts, if A is in, let's say, B and B is in C, if they're not in the same part of the relation, here's our negative contradiction, then A minus 2.5 times B minus 2.5 is strictly less than 0. So AB is not in R. So if AB is in R, then they're in the same part of the partition. Okay. Then next we have if A and B are in the same part of the partition, if they're in A1 or A, B are in A2. Well, I'm going to say these in words. So if they're in A1, then you know that A is less than 2.5 and B is less than 2.5. So A comma B, AB is in the relation since A minus 2.5 is negative and B minus 2.5 is negative and their product is positive. If they're in A2, then you know they're bigger than 2.5. So A minus 2.5 is bigger than 0 and B minus 2.5 is bigger than 0. So that case, it's positive again. So if they're in the same partition, part of the partition, then AB is in the relation. Okay, so we have that AB is in relation if and only if it's the same, it's in the same part of the partition A1, A2. Okay, so we found the partition. Now we can prove it's an equivalence relation by proving it's reflexive, symmetric, and transitive. So what did we have out of that? We had R was equal to B union C. And B is equal to 1, 1, 1, 2, 2, 1, and 2, 2. And C is equal to 3, 3, 3, 4, 3, 5, 4, 3, 4, 4, 4, 5, 5, 3, 5, 4, and 5, 5. Okay, so we know that the relation is equal to that because we did that before. So symmetric, no, reflexive. Well, just looking at it, we can see that, but otherwise we'd say, is A in R? That's our question for all A. Well, if A is an element of B, then A minus 2.5 times A minus 2.5 is equal to negative times negative, which is greater than or equal to 0. If A is in C, then A minus 2.5 times A minus 2.5 is equal to positive times positive, which is also greater than or equal to 0. So AA is in the relation. Do you all understand how we did that? Okay, symmetric. A, B in R means A minus 2.5 times B minus 2.5 is greater than or equal to 0. Then B minus 2.5 times A minus 2.5 is greater than or equal to 0 by commutativity of multiplication of, well, you can say rationals or real numbers. Either one. Okay. So the last one is the more interesting, transitive. So we have AB in R and BC is in R. And then we want to show AC is in R. We haven't gotten there yet. So what do we say? We say AB in R means A minus 2.5 times B minus 2.5 is greater than or equal to 0. So that means they're in the same set of B or C. I'm sorry, of A1 or A2. Okay, that means so either A1 and I'm sorry, A and B are both less than or equal to 0, or A and B are both greater than 0. Both. And then BC in R implies A minus 2.5, B minus 2.5 times C minus 2.5 is greater than or equal to 0. So either B and C are less than or equal to 0, or B and C are greater than 0. Now, we don't know which, it doesn't matter. But both of those tell us then A, B, and C are either all greater than 0 or all less than or equal to 0. Because B has the same sign as both A and C. So that means they're all the same. So that means that A and C have the same sign. And if A and C have the same sign, then, I'm sorry, they're not all greater than or equal to, 2.5 or 2.5, 2.5, 2.5. They're either both less than 2.5 or greater than 2.5. Yes, I do indeed. Okay. So either greater than 2.5 or all less than or equal to 2.5. So if that's the case, then A and C have the same sign, and then have the same sign with respect to 2.5. So then A minus 2.5 is either positive or negative, but whatever that is, C minus 2.5 is the same. And so the result is greater than or equal to 0, and A, C is in the relation R. Now, would you have something this complex to prove on an exam? On a homework? Definitely. On an exam? Well, you certainly wouldn't have to prove both directions. It takes time to do this, but it's not that bad, is it? I'm sorry we're a little late, but you can have your 5 minutes right now. Okay, we're back. Just wanted to go back to the first problem that we looked at with showing the inverse. And the issue is here. We had that G of M was equal to minus M over 2 if M was even, and M plus 1 over 2 if M was odd. So we'd say, suppose Q is positive and even. That was the question. And we wanted to say, is there an M that maps onto it by G? Okay. And here's my Q. That's what we have. And the M is equal to 2Q plus 1. Two Q minus 1, sorry. Okay. So I've picked a positive even number. If I pick a positive odd number, a negative, positive even, positive odd, it doesn't matter. Okay. Every positive number in the codomain of G, okay, is mapped to by that. And every negative number in the codomain of G is mapped to from that. So they're both mapped from the natural numbers. Okay. The confusing part of that is that we were looking at the definition of F, not the definition of G when we looked at it. So what we're looking at is saying, okay, now remember, G maps from N to Z. And it maps from N to Z by saying all of the odd numbers map to positive and all of the even numbers map to negative. Okay, we didn't have that right before. Now we do. I hope that helps. Okay, let's catch up to where we should be now. Okay, we did that. Good. Let's look at another problem, and I like this one. It's a little different. So we have 4 people lined up at a restaurant, socially distanced, of course. They want to enter it. Actually, they're going to eat outside. There are 24 different orders that they can be standing in line. Okay, and here are the orders: A, B, C, D, and B, C, A, D, and go through them any way you want. Now, when they're seated at a table, that order means less in the sense that if I sit them around the table and I count the order in counterclockwise direction, I have A, B, C, D, and that's the same as B, C, D, A, and that's the same as C, D, A, B, etc., and D, A, B, C. Why? Because if I look at B, he only sees A and C. And if I look at C, he only sees B and D. And he always sees B on the left. He always sees D on the right. Okay? So we're looking at this and saying, well, if I'm in a straight line, there are 24 different ways they can be lined up. But when they're sitting at the table, there are a bunch of these lineups that turn out to be the same. So here's my question: which ones are the same, and how do we group them? Okay, and so the equivalence relation on the set of all of these arrangements. So we have the linear arrangement when they're in line, and we have 24 of them. And now when I want to take them and create equivalence relation, an equivalence class that says, if each person has the same person to their left and right, then it's the same arrangement, even if it's different when they're standing in line. So what do we have? Well, the easy one is to say we have A, B, C, D. That's the picture we have. And that's the same as B, C, D, A. And that's the same as C, D, A, B. And that's the same as D, A, B, C. Okay, so all we're doing is saying we're changing the person we start with and then just going round counterclockwise until we arrive back at the same one. And then each person has the same person on their left and right. So now, what do we have here? We took away A, B, C, D. And we took away B, C, D, A. And we took away, I got to have C, D, A, B somewhere. Where's C, D, A, B? C, D, A, B. I took away that. And then I took away D, A, B, C. So they're all accounted for. So what do we do next? Next, we say, okay, pick one of the others. How about A, B, D, C? And then we go round robin again. Who do we start with? Well, here we'll start with B, D, C, A, D, C, A, B, C, A, B, D. Am I right? Yeah. So where are we now? A, B, D, C, that's that one. B, D, A, C, that's that one. D, C, D, C, A, B. There we go, that one. And C, A, B, D, C, A, B, D, that one. We use that up. Okay, so remember, in this arrangement, everybody sees the same person to their left, the same person to their right. In this arrangement, the same thing is true, and they're seeing different people. And then we move on. Let's pick another one. A, C, B, D. Then C, B, D, A. Then B, D, A, C. And then D, A, C, B. So they're all the same again. So this was A, C, B, D. Then we have C, B, D, A, C, B, D, A. And then we have B, D, A, C, B, D, A, C. Where are you, B, D, A, C? Yeah. B, D, A, C. Nope. Where's B, D, A, C? It's got to be here.
I think you crossed it out already. You
I
mixed it
did.
out.
And we have D, A, C, B. This one. Okay, well, I hope you're right. If not, we're going to wind up with one not crossed out at the end. Okay.
I know which one's not crossed out. It's BDCA.
BDCA, but that's not used yet. Is it?
It was used in the second set.
Ah, I screwed up. I crossed out the wrong one, huh? Yeah, don't make those mistakes. Okay, I'm going to leave you do the rest of this yourself. You do the last three. Okay. That forms an equivalence relation. Why? Because it creates a partition on the set of all arrangements. Each arrangement falls into exactly one of those groups. Okay? Okay, and two arrangements are related, namely they look the same if and only if, that's how we figured them out, if I didn't make mistakes. They're in the same grouping, the same part. So that creates, yes, Dane.
So if I can partition a set like this, does that mean I have some equivalence relation that it
Absolutely.
induces?
Absolutely. You're defining, when you create a partition, you are defining an equivalence relation. That's an if and only if. That's the definition. Okay?
Thank you.
So if I tell you to partition the integers by one set is all the evens and another set is all the odds, what's the equivalence relation that I created? The equivalence relation is that A and B are related when B minus A is equal to 0 mod 2.
So is that just the same as saying B minus A is divisible by 2?
Yeah, absolutely. Remember what mod means. Mod means the remainder. Okay? Good. Proof that a relation R, if a relation R is symmetric, then it is its own inverse. What would we have to do to prove this? Yes, Christopher.
So I have a quick question about the previous example. So when we're asked to give that relation, what you wrote there, the sets of those
Yes.
arrangements, that would be an acceptable definition for the relation.
Yeah, well, yeah, you say that I would define the relation. The relation is defined that way. Okay. You can also define a relation by grouping them like that, but it's uglier. Okay.
Okay, thank you.
How would we prove that a relation is its own inverse? Remember, what you're trying to say is that R inverse is equal to R. And remember, R inverse and R are both sets in A cross A, whatever A is. So that means you're proving, to prove R inverse is a subset of R, if you think of the pairs as the sets, and R is a subset of R inverse. And you saw just set stuff would go away at the end of chapter 3. No. Okay, that's what we have to prove. Okay, how are we going to do this? Ideas?
Maybe an element-wise proof.
Yeah, absolutely. So we would start out and we say let A be an element of R inverse. We want to prove R inverse is a subset of R here. Okay. By definition, BA is in R. That's how the inverse is defined. We just flip the order of inverse. Now we have but BA in R and are symmetric. This is the biggie. Means AB is in R. So we started out saying let AB be in our inverse, and we've shown that AB is in R. So R inverse is a subset of R. And I'm going to let you do the other direction yourself. But remember, we start that out by saying let A, B be in R. And now we have to prove AB is in our inverse. Okay, I'm going to let you do that yourselves. And I think today we're done. I want to remind you again, homework is due tomorrow night. Exam next Thursday. On Tuesday, we'll start talking about combinations. And we're done. I'll answer any questions. I'll stay after and answer any questions anyone has, okay? If you want to work on this problem and then ask me about it now, that's okay. We can do that too.
Thanks.
Thank you all for coming. David, you have a question?
Yeah, I'm still kind of confused on that earlier thing we did. The Q is positive.
Yeah.
I didn't quite catch how you explained that. It was kind of.
You thought I just whipped it around and I think we're back here.
Yeah.
Okay. Well, we have G as a mapping.
Yeah.
And we said, let Q be a positive even number. Okay. Actually, Q can be any positive number, but that's fine if you like it to be even.
Yeah.
Okay, now remember, G maps onto Z. Okay. Now, G starts out and says, I'm going to map onto Z. So I'm going to map some things from the natural numbers onto the positives and some things onto the negatives. So we look and we say, well, whatever we just did, we mapped onto the positives. Okay. So then we look back here and we say, this maps positive onto positive. This would map positive onto negative, and that's not what we have. Okay. So Q is positive. So M was a positive odd number that mapped onto it. And then we figure out what M is.
Okay. I think I'm starting to see how it works because G of M doesn't have to be a function because it's a relation.
G is a function. This is absolutely a function. If it's an inverse, it's a function. If it's an inverse relation, it's not a function. Okay. There are many functions that do not have inverses, but this does. Okay. We pick an arbitrary element of Z. Then that element is either positive or negative, right? If it's positive, it's the image of a positive number under G. If it's negative, it's the image of an odd number in G if it's positive. If it's negative, it's the image of an even number. Okay?
Yeah. Okay. I think I'm starting to see it now.
Okay. So you have to look at what you're mapping. You sort of say, I've got this mapping. And basically what it's saying is, here's an even number. I'm mapping it to 0, 0. Here's 1. I'm mapping it to, what am I mapping 1 to? Map to
1. 1 maps to 1, I think.
Well, let's look a second. Here's G. G is mapping. So G says if M is odd, there we go. 1 is odd. It maps 1 plus 1 over 2 divided by 2. Okay, 1 maps to 1.
But then 3 maps to 2. 5 maps to 3.
And that maps to 2 maps to negative 2 over 2. That maps to minus 1.
Yeah.
Then I look at 3, and that maps to 3 plus 1 over 4 over 2. And then I look at 4, and that maps to minus 2. Does that make sense now?
Yeah, and the only thing I think, thinking now about it, we probably also need is equal to 0 if it's 0. But besides that, that covers the entire spectrum right there. It's just the fact that infinitely, like, you're way
Yeah.
farther ahead in the natural numbers than you are in the Z. Like,
Yeah, it's hard to get that, but that's one of the things. You can also prove that the integers have the same cardinality as the rational numbers,
yeah,
and
Because
that's
they're
even
all in
more
there.
confusing.
yeah. Okay, yeah, that makes a lot more sense now. Thank you so much for that.
It's my pleasure. Are there any other questions? Does anybody else want to start the last or finish the last problem we talked about?
Would the irrationals have a different cardinality than Z?
Oh, yes.
Does it have to do with whether it's countable?
Yes. Countable equals the same cardinality as the natural numbers.
And uncountable is anything else that's infinite.
Well, there are actually levels of cardinality. But it's called Aleph 0. That's the the Hebrew Aleph. Aleph 0 is the cardinality of the natural numbers. Aleph 1 is the cardinality of the reals and the complex and the n-dimensional reals. But remember, we have a theorem that says every set and its power set have different cardinality.
But you can always go up in cardinality.
Yeah, but I don't ever remember dealing in my practical life other than theory with anything that's beyond Aleph 1.
Okay, thanks.
Okay. Anything else? Okay, we're done for the day.